Welcome to the Practical Phi. In this tutorial, we are going to study about 2D simulation using example of a 2D triangular plate. So before going to that, let's understand what's a 2D simulation. So in real world, everything is 3D, right? And there's no such thing as a 2D bodies. Some problems, however, can be simplified and simulated in the 2D spaces. So a structural mechanics problem can be considered to be two-dimensional if we are able to make a reasonable assumption about variation of unknown parameter in a third dimension, right? So for third dimension, if you can make some good assumption, then we can simplify that 3D problem into 2D case. So three practically important situation of these types arising as structural mechanics. So basically the first one is this kind of cases. This structure is very thin as compared to other two dimension and is loaded in its own plane. So example is some rotating impeller wheel. So thus an top and bottom faces are free from any normal stress in Z, right? So because a thickness is very small. So as a thickness of very small, then we assume that the stress is in across the thickness there is zero throughout. So as a shearing stress, tau xz and tau iz also. The only non-zero stresses will be then in normal stresses will be sigma x, sigma y and shear stress tau xy. So the stress strain relationship and this kind of simplification where two other dimension in x and y are large as compared to third dimension. So this kind of condition is known as a plane stress, right? So when two other dimensions are large as compared to third dimension, then third dimension variation of stresses can be considered as a zero. We assume the sigma z is a zero throughout. So the stress strain constitutive relation for this kind of we'll assume that it's a linear elastic isotropic material. Then the relation can be represented as shown here. So it will have a three component of stress: sigma x, sigma y and tau xy, right? Others like tau xz, tau yz and sigma z will be zero as this third dimension is very, very small. Where you can see here it's a strain zero, so this it's initial strain before any loading. The next case is of a plane strain kind of thing. The second case is known as a plane strain. The picture depicted in this case is other extreme of the first case. So in first case there was a third dimension was very, very small, and in this case the third dimension is reasonably large. So in here in this rod, the length of member is so long that it is reasonable assume to that the strain, longitudinal strain in this length direction, which is very, very large, is to be zero, right? So example is torsion of uniform shaft, right? So if you are testing it, the strain along Z, along the length will be very small. So as to shearing strain also, gamma xz and gamma yz, so only strain will be the torsional strain or torsional stress will be there in xy plane along the rotation axis. So the stress strain constitute a relation for a linear isotropic elastic material can be given like this, right? And again epsilon raised to 0 is initial strain. So Here you have to observe that the normal stress sigma z is non-zero, but can be readily obtained from the condition that longitudinal strain is 0 in z direction. Now there is a third case. We have seen a plane stress, we have seen a plane strain. Third case is of axisymmetry kind of problem. So in axisymmetric body, which is subjected to axisymmetric loads, like a pressure load or some kind of that, the all particle with the same radial and axial coordinates, that's r and z, shares the same behavior regardless of tangential coordination. So we are eliminating here the tangential coordinate, and we can reduce this problem into 2D kind of problem. So its most important class of problems, commonly we tell this problem as axisymmetric problems. So examples are pressure vessels. If the geometry of structural, material property, support conditions and loadings all are axisymmetry, then it is generally reasonable to assume that the resulting output deformation will be also axisymmetry, right? So if we'll have a cylinder, right, so we'll consider a cylinder, thin cylinder, which is subjected to internal pressure of same amount, right, and same, all other properties are same. Then if it is deforming in at 0 degree in by some x amount, then at 90 degree also it will be deformed by same amount, at 180 degree, at 270, and at any angle across the theta it will be same. So in tangential direction, variation is not there. So the reasonable assume that resulting deformation will be axisymmetry, that it will not vary along the circumferential direction. Thus it is sufficient to determine the variation of unknown field variable. Example can be deflection or temperature in any one plane as shown in figure. In practical pressure vessels, there are minor geometrical features which can deviate the perfect axisymmetry body, such as some kind of threadings are there at the top or those kind of things, but we will neglect those things, very small details, because it will not affect the overall integrity of the structure, right? So in axisymmetry kind of the relations are given like this, is shown on screen. Sigma r radial stress, sigma theta, sigma z, and sigma rz, right? So these are the stresses which we can find out in axisymmetric example. The problem which we are going to take is of a plane stress kind of things, right? So other two dimension in x and y will be larger than the thickness dimension, and we'll assume that the sigma z is 0 in this case. So this is a problem, a 2D triangular plate. This problem we are also going to solve using FEM approach, how answers do in a background, that we are also going to see by hand. So a triangular plate which is made up of steel having Young's modulus of 210 gigapascal, Poisson's ratio of 0.3, thickness is 10 mm as shown in figure. So it's a 20 by 30 triangular plate. This 20 side is a fixed, this side is fully fixed, right? The displacement at this third node is 1.95 into 10 to the power minus 4 mm in x direction, and minus 1.114 in y direction. So resultant, it might be like acting like this respectively. So we have to determine the elemental stresses, right? So what stresses will be there? Sigma x, sigma y, right? Sigma there will be there. Yes, sigma z won't be there because it's a plain stress kind of assumption we are going to make. So the third component of stress will be 0, right? There will be tau xy shear stress, obviously. So let's see how we can solve this in answers. So you know how to open the answers workbench, so and how to select a static structural one. So let's open directly static structural screen in next video.